Welcome to the e-learning course on cybersecurity for operational technology (OT) professionals. This course provides guidance on how to secure operational technology while addressing their unique performance, reliability, and safety requirements. OT encompasses a broad range of programmable systems and devices that interact with the physical environment or manage devices that interact with the physical environment. These systems and devices detect or cause a direct change through monitoring and/or control of devices, processes, and events. Examples include industrial control systems (ICS), building automation systems (BAS), transportation systems, physical access control systems (PACS), physical environment monitoring systems, and physical environment measurement systems. This course provides an overview of OT and typical system topologies, identifies typical threats and vulnerabilities to these systems, and provides recommended security countermeasures to mitigate the associated risks. This course comprises the following modules. Module 1, Industrial Control Basics. Module 2, Industrial Cyber Threat Landscape. Module 3, The Value of Industrial Frameworks. Module 4, Best Practices for ICS Decision Makers, and Module 5, Your ICS Cybersecurity Action Plan. Let's begin with Module 1. By the end of this module, you will be able to identify the three measurements that dominate OT cybersecurity conversations, identify the critical infrastructure sectors, list the difference between IT and OT cybersecurity challenges, identify the three classes of ICS, recognize the importance of the Purdue model, list the cybersecurity risk factors, and recognize the key terms and definitions in the industrial cybersecurity field. Almost every single aspect of modern life depends on the uninterrupted functioning of industrial control systems (ICS). ICSs are responsible for keeping lights on, ensuring clean drinking water, as well as providing other essential infrastructure processes. Beyond power, energy, and other utilities, ICSs are also responsible for the manufacturing of your computer, your car, as well as countless other physical items that we use every day. It's imperative that ICSs are guarded against all cyber events, accidental or malicious, as the physical ramifications of such events pose major threats to both public safeties as well as to any industrial entity's ability to stay operational and competitive. As ICS equipment becomes more and more Ethernet connected, they also become highly vulnerable. By and large, industrial organizations are not ready for the digital convergence of their IT as well as OT environments. The rate of newly connected devices is overtaking the rate of device security. Physical equipment that was once considered only mechanical is now becoming part of the fast-growing world of the Industrial Internet of Things, IIoT. Although having smart machinery improves efficiency, but without the proper precautions, it also offers cyber criminals remote access as well as attack opportunities they didn't have before. What is an ICS? Industrial Control System (ICS) is used as a generic term that has several types of control systems that include supervisory control and data acquisition (SCADA) systems, distributed control systems (DCS), as well as other control systems such as programmable logic controllers (PLC). These control systems are used in discrete manufacturing, process automation, energy, and transportation verticals, many of which operate critical infrastructure. An ICS includes combinations of control components, for example, electrical, mechanical, hydraulic, and pneumatic, that combine to operate and control a physical process such as those found in many industries like automotive, petrochemical, manufacturing, oil and gas, food and beverage, as well as in power generation, transmission, and distribution. While OT and IT are both required to guard their systems and data from compromise, OT cybersecurity professionals tend to approach their systems differently than traditional IT as they have varying priorities. For example, ICS control engineers can be reluctant to upgrade their equipment even when it would improve their cybersecurity outlook. This is due to their focus on maintaining constant uptime and measuring performance characteristics such as overall equipment effectiveness, OE, rivals, and other priorities like making sure they are running the latest and greatest firmware. The three imperatives that tend to dominate the OT cybersecurity conversation are safety, quality, and uptime. Let's look at each in detail. Safety. Cyber attacks or human errors in an ICS context can result in real-world physical consequences. On the other hand, a customer data breach could cost a retail company millions in fines as well as damage their reputation. The physical safety of human beings isn't the main factor. In industrial environments, however, safety is crucial. This consists of the safety of the workers on the plant floor and the customers served by the output of a particular ICS. Safety in ICS context looks like shipping uncontaminated ingredients from a food processing plant or delivering a functioning car airbag within a vehicle built in an automotive assembly plant. Quality. Irrespective of your end product, any threat to its quality could result in financial loss. Cyber events that don't risk the physical safety of workers or customers can still have a negative effect on industrial organizations in the form of lost products due to quality inconsistencies in the form of scrap or recalls. The ability to detect and correct anomalies affecting quality is key to ICS process integrity. Uptime. Cyber events can financially affect industrial organizations in numerous ways, right from the theft of intellectual property to a denial of service (DOS) attack that renders parts of the control system unusable for a time period. To put the importance of uptime in perspective, the manufacturing industry observes annual losses of $50 billion due to unplanned downtime. Several industrial devices are getting older. Operators often feel that they can't shut down these systems for routine maintenance to enhance security as they are essential for the whole operation of the service or plant. There's also the concern that an upgrade/update might disturb operations. In a few cases, security vulnerability scans, typical in IT environments, are too troublesome to use in OT environments. In fact, many ICS environments still possess specialized industrial protocols and equipment that don't make use of TCP/IP, the most common communication protocol for IT networks and security tools. Even when organizations can overcome these hurdles, cybersecurity is a relatively new discipline for operations teams running an ICS environment. They may choose to delay acting on security issues due to genuine concerns about safety, quality, as well as uptime. While such concerns are understandable, cyber attacks against critical infrastructure are increasing. Critical infrastructure keeps the world running by providing basic services such as water treatment and electricity. The U.S. Department of Homeland Security's National Infrastructure Protection Plan divides critical infrastructure into distinct sectors. There are 16 critical infrastructure sectors whose assets, systems, and networks, whether physical or virtual, are considered so vital to the United States that their incapacitation or destruction would have a debilitating effect on security, national economic security, national public health or safety, or any combination thereof. Let us now look at the different critical infrastructure sectors. Chemical, commercial facilities, communications, critical manufacturing, dams, defense industrial base, emergency services, energy, financial services, government facilities, food and agriculture, healthcare and public health, information technology, nuclear reactors, materials, and waste, transportation systems, water and wastewater systems. Not all ICS-based organizations are serving as the backbone of public safety, but they need to be secured. Common verticals include automotive manufacturing, power generation, transmission and distribution, oil and gas, pharmaceutical manufacturing, and water or wastewater. Until recently, disparate network types such as Ethernet and Fieldbus didn't mix. At present, ICSs are increasingly enmeshed with IT devices and business processes, boosting the risk of compromise to their command and control functions. The IT/OT convergence requirement also poses several questions for business unit owners, especially those whose responsibility is ICS cybersecurity, either the plant floor operator or the IT Security Operations Center, SOC. The answer, of course, is that the responsibility is shared. Once you clearly define roles and responsibilities within your overarching IT/OT cybersecurity program, you can run into several technical obstacles in bringing these two sides together. This is because that legacy ICS equipment is now increasingly Ethernet connected, the credit goes to the IIoT, which wasn't made to manage data transmission securely. The U.S. Department of Homeland Security's breakdown of the distinction between different security controls on the shop floor versus the top floor. Let us now understand the IT and OT cybersecurity challenges for each security topic. Antivirus and mobile code. Information technology, IT, very popular, can be easily deployed and updated. Users can change customization and can be asset-based or enterprise-based. Operational technology, OT. Memory requirements can affect ICSs. Organizations can only guard legacy systems with aftermarket solutions, usually needs exclusion folders to avoid programs quarantining critical files. Patch management. IT. Easily defined, enterprise-wide, remote, and automated. OT. Long timeline for successful patch installation, OEM-specific, may break ICS functionality. Asset owners need to define acceptable risk. Technology support lifetime. IT. 2 to 3 years, multiple vendors, ubiquitous upgrades. OT. 10 to 20 years, usually same vendor over time. Product end of life creates new security concerns. Testing and audit methods. IT. Use modern methods and systems that are resilient and robust to handle assessment methods. OT. System tune testing. Modern methods can prove to be inappropriate. Equipment may be inclined to fail during testing. Change management. IT. Regular as well as scheduled, aligned with minimum use periods. OT. Strategic scheduling, a non-trivial process as its impact on production. Asset classification. IT. Common and performed annually, results drive expenditure. OT. Only performed when obligated, accurate inventories unusual for non-essential assets, disconnect between asset value and appropriate countermeasures. Incident response and forensics. IT. It can be easily developed and deployed, and some regulatory requirements are embedded in the technology. OT. Focused on system resumption activities, forensics procedures that are immature, beyond event recreation, need a good IT/ICS relationships. Physical and environmental security. IT. Can range from poor office systems to outstanding critical IT operations systems. OT. Usually excellent for critical areas, maturity differs for site facilities based on criticality/culture. Secure systems development. IT. An integral part of the development process. OT. Historically not an integral part of process development, vendors are maturing but at a slower rate than IT. Core/flagship ICS solutions are hard to retrofit with security. Security compliance. IT. Definitive regulatory oversight based on sector and does not include all sectors. OT. Specific regulatory guidance based on sector and does not include all sectors. Most ICSs operate on one of the following types of systems: distributed control systems, programmable logic controllers, supervisory control and data acquisition. Let's look at each in detail. DCS. Distributed control systems, DCS, manage and automate thousands of control points inside a process. DCSs are often made up of numerous components, such as controllers, I/O devices, and servers. These are usually present in large localized facilities like oil and gas refineries, chemical, pharmaceutical, and power generation plants. PLC. A programmable logic controller, PLC, is the kind of industrial computer that controls the operation. It makes decisions through input received by sensors and then through logic. Programming decides what to do, e.g., turn on a motor or release pressure. PLCs are used within any industrial automation process and can also be part of a larger system, such as a DCS. SCADA. A supervisory control and data acquisition (SCADA) system centrally controls and monitors remote field devices that are often spread across thousands of square miles. It can control remote field devices to perform certain operations depending on specific alarm or notification conditions, like opening a valve or closing a breaker. For geographically dispersed control environments, such as those of a natural gas pipeline or remote electrical substations, a SCADA system is used to control and manage these applications. During the early stages of IT/OT convergence, it was clear that a reference architecture was required to articulate roles and functions of the machines that manage the physical processes and the other relevant ancillary devices and operations. In 1990, the Purdue Enterprise Reference Model was built to do just this. Today, it is referred to as the Purdue Model. The Purdue Model has matured over the years, but its purpose of classifying various management domains for physical processes remains as it is. Over its growth, the Purdue model has become the gold standard for network segmentation. This means that network segmentation supports different levels of the model through the use of firewalls, where all traffic is denied traversing the Purdue model levels unless it's explicitly permitted. As several connectivities were occurring between the shop floor and business IT networks, the Purdue model grew to outline a new line of distinction between industrial control networks and enterprise networks through the use of a demilitarized zone, DMZ. Today, the Purdue model has 7 levels, including the DMZ at level 3.5. Levels of the Purdue model. Level 0 I/O field devices. Level 1 control, PLCs and RTUs. Level 2 process, HMIs, operator stations, and supervisory control. Level 3 operations, historians, network services, and advanced control. Level 3.5 DMZ. Level 4 business network. Level 5 enterprise IT. Industrial specific equipment and devices are available as you get closer to the physical process at level 0. As such, level 0 and level 1 are where devices like sensors, actuators, drives, DCSs, and PLCs reside. As you move further from level 0 and level 1, more standardized, traditional IT systems, like engineering workstations, human-machine interfaces, HMIs, SCADA, and data historians, will be found. All of these are working on common operating systems, like Linux as well as Microsoft Windows. Cybersecurity was far from the radar when modern-day ICSs first developed over 30 years ago. In addition to IT/OT convergence, industrial organizations have to overcome a few other challenges to stay protected from errors and attacks. The shift to new network technologies enhanced data collection, operational efficiencies, new levels of automation, as well as time to market, but it also produces new cybersecurity risks due to factors like unintegrated technologies, flat networks, as well as workforce challenges. Let us now look at each of the ICS environment factors. Unintegrated technologies. Several ICSs are purpose-built and proprietary, and the creation of these ICSs technologies took place when cybersecurity impacts were not a concern. Flat networks. Several ICS networks are flat, meaning each device is accessible to the rest. Within a flat, non-segmented network architecture, a malware attack against a single device gives the malware free rein to spread through the control environment with impunity. Workforce challenges. With an aging workforce and an increase in the adoption of new technologies within ICS at a much higher rate than ever, a skills gap for securing ICS has arisen. With an estimated 3.5 million unoccupied cybersecurity jobs by 2021, the skills gap is another obstacle to tackle. Here is a quick recap of what we covered. Almost every single aspect of modern life depends on the uninterrupted functioning of industrial control systems. Beyond power, energy, and other utilities, ICSs are also responsible for the manufacturing of computers, cars, as well as countless other physical items that are used every day. It's imperative that ICSs are guarded against all cyber events, accidental or malicious. Critical infrastructure keeps the world running by providing basic services such as water treatment and electricity. Industrial control system is used as a generic term that has several types of control systems, which include SCADA systems, DCS, as well as other control systems such as PLC. The Purdue model is the gold standard for network segmentation. And the shift to new network technologies enhance data collection, operational efficiencies, new levels of automation, as well as time to market, but it also produces new cybersecurity risks due to factors like unintegrated technologies, flat networks, as well as workforce challenges. Congratulations! You successfully completed Module 1 of the Cybersecurity for Operational Technology Professionals course.